Section 19 of the Science, History of the Universe, Volume 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science, History of the Universe, Volume 2, edited by Francis Rolt-Wheeler, Geology, Chapter 10, Reconstructive Processes. It has been pointed out in the work of destruction that in the true sense of the word it is not destruction at all, but rather a preparation for building anew. It is at the same time the closing of one period of existence for a certain group of particles of matter and the beginning of another. But while the active agencies that lead to the breaking down of former masses are numerous, in the strict sense of the word, the reconstruction agency is only one, that of sedimentation. The new rock is built out of the old, though under differing conditions and with different results. At the present time, it is estimated that about 1/2 of the waste of the land is carried directly into the sea, while the remainder is arrested in its journey and deposited upon the land. The accessible rocks of the Earth's crust are more largely composed of marine deposits than those laid down in other ways. Yet the non-marine sedimentary rocks are also extensively represented. A natural division of the sedimentary accumulations is into the marine and the continental, including in the latter the deposits which are made upon the land, or in such bodies of water as are not parts of the sea. It is an almost universal characteristic of sedimentary accumulations, says Scott, whether modern deposits or ancient rocks, that they are stratified, that is, divided into more or less parallel layers or beds. Stratification is due to the sorting power of water, or of the wind, by which, so long as conditions remain the same, particles or fragments of similar size and weight are thrown down at the same spot. Layers clearly demarcated from one another may be produced in either one of two ways. 1. By such a change of conditions that the material deposited changes abruptly, though perhaps only as a mere film of a different substance, or 2. By pause, however brief, in the process of deposition. The planes of contact between successive layers, which may be indistinct or very sharply defined, are called the bedding or stratification planes. Each bed is made up of some predominant substance in a state of greater or less purity, such as gravel, sand, or clay, due to the sorting powers of the water, and thus heterogeneous material is separated into its constituent parts, though the separation is rarely quite complete, and sometimes there is hardly any separation at all. In the sea or a large lake, the material on the bottom grows finer outward from the shore, while a river, whose velocity diminishes from headwaters to mouth, lays down material of decreasing coarseness from the boulders and cobbles of the headwaters to the fine silt of the lower course. Wherever a sandy soil occurs unprotected by vegetation, as in deserts or along the seacoast, the wind drifts the sand and piles it up into hills or sand dunes. When the sands are mixed with pieces of shells or other calcareous material, percolating waters, by dissolving and redepositing the carbonate of lime, may cement the sands into firm rock. This is more conspicuous when the whole material is calcareous, as in the shell sands of Bermuda. Springs also form siliceous deposits, but they are rare, and the carbonate of iron is deposited as chalybeate. Phosphate deposits are also made in rainless regions, where guano, the accumulated excrement of birds, piles up to great thickness without the loss of its soluble matter. Cave deposits are usually chemically formed, and are due to the solution and redisposition of carbonate of lime. At first the deposit is white, opaque, and very friable, crumbling at a touch, but repeated depositions fill up the interstices of the porous mass and convert it into a hard, translucent stone, which assumes a crystalline structure through the development of calcite or aragonite crystals. The masses thus formed that depend from the roof of the cavern are called stalactites. After hanging for a time from the roof, the drop of water falls onto the floor of the cave, and there, in similar fashion, deposits a little layer of carbonate of lime, which gradually grows into a cone. This is a stalagmite, and differs from the stalactite only in the fact that it grows upward from the floor, instead of downward from the roof. The stalagmite is, of course, exactly beneath the stalactite, and as long as the water continues to follow the same path, the two cones are steadily, though very slowly, increased both in height and thickness, until they meet, unite, and form a pillar extending from the floor to the roof of the cavern. These deposits form the curious and beautiful features of limestone caverns. The vegetable accumulations are the most important of the swamp and bog deposits, for the preservation of which a certain amount of water is necessary. The vast quantities of coal which occur in so many parts of the world testify to the significance of the part which bog and swamp accumulations of vegetable matter have played in the earth's history. The nearest approach to coal in process of formation at the present day is in the peat bogs, which are especially abundant and extensive in cool, damp climates, as in Ireland, Scandinavia, and the northern parts of South America. The Great Dismal Swamp of Virginia and North Carolina probably more nearly reproduces than do most existing peat bogs the condition of the ancient coal swamps. The swamp, which measures 30 miles by 10, is a dense growth of vegetation upon a water-covered soil of pure peat about 15 feet deep and with no admixture of settlement. The swamp cypress grows abundantly in the bog and prevents, by its dense shade, the evaporation which would take place in summer could the sun's rays penetrate the wet soil. The shallow layer of water which covers the ground receives the fallen leaves, twigs, and branches, and sometimes even the trunks of fallen trees, preventing their complete decomposition, while the dense covering of mosses, reeds, and ferns which carpet the ground add their quota to the mass of decaying vegetable matter. The accumulations at the mouths of rivers, generally known as deltas, have, from ancient times, been the means of showing man in what manner the configurations of the surface of the earth was changing. The delta at the mouth of the Nile is a typical case in many ways, and its working was observed by the older nations that bordered the Mediterranean. This is more especially noticeable in the Nile, for there was added to the problem the question of why the delta did not advance further into the sea due to a swift current along the seafront, and this led to an investigation of the Mediterranean currents. But the delta of the Mississippi, on the other hand, is advancing rapidly, about 110 yards a year, or 27 feet a month, a speed which, if to be extended to long geological ages, is amazing. Extraordinarily though it may seem, a week's stay at the mouth of the Mississippi is enough to see perceptibly the surface of the earth changing shape. Debris brought down by the Indus, a swifter stream, instead of forming a delta with a sluggish current, has been carried to the ocean, where it has made a shoal covering an area of 700,000 square miles, a little larger in size than all the states north of Mason and Dixon's line and west of the Mississippi, or 5 times as large as the British Isles. In the course of time, this shoal will rise to the surface, and a new country will have been formed. The delta formation is seen in small streams entering lakes, and accumulations in the same manner as are made in the ocean beds are to be found in the lake basins. In small lakes, the coalescence of deltas, or the advance of a single one, will eventually fill up the basin, forming first swamps, and then smooth, grassy meadows, through which flow the streams, keeping their own channels clear. Such filled-up lakes are common in many mountain valleys. Lake deposits betray the form of the basin in which they are laid down. Around the old shoreline are masses of coarse materials, with deltas interspersed to mark the mouth of the streams, while toward the middle of the basin quantities of fine mud and clay have accumulated. An excellent example of such a deserted lake basin is that known as Lake Bonneville in Utah, of which Salt Lake is the shrunken remnant. The drying up of this lake, which was once fresh and had an outlet northward to the Snake River, is an event geologically so recent that its form and size, its shores and islands, its high and low stages, in short, its history, can be made out with great clearance, as has been admirably done so by Mr. Gilbert of the United States Geological Survey. At its time of greatest extension, Lake Bonneville had an area of 19,750 square miles and a maximum depth of 1,050 feet, while Salt Lake, which is variable, had, in 1869, an area of 2,170 miles and an extreme depth of 46 feet. Around the ancient shores are reserved the terraces, embankments, and deltas of the various stages of water, which the gravels and the sands appropriate to the shallow water. The sea is the great theater of sedimentary accumulation, says W. B. Scott in his Introduction to Geology, and rocks of marine origin form the larger part of the present land surfaces. Important as other classes of deposits may be, they are less so than those laid down in the ocean and the waters immediately connected with it. Marine deposits may be classified primarily in accordance with the depth of water in which they are laid down. One of the most valuable guides to the history of ancient rocks, and secondarily in accordance with the nature of the materials of which they are composed and the processes by which they were accumulated. Ripple marks are formed by the wind or by the rippling movements of water, and may be seen on any sandy beach. They occur especially in sands, in shoal water deposits, as well as in those made on floodplains and in lakes and on sand dunes. They are found in rocks of all geological periods, and though most frequent in sandstones, occur in other kinds of rocks. Wave marks and rill marks, sun cracks, rain prints, and the tracks of land animals are preserved in a similar way. It might seem incredible that such slight marks could be preserved for ages in the solid rocks, were it not for the fact that their occurrence is so common. Where for long distances no large rivers enter the sea, and the material is all derived from the wear of the coast, the arrangement of coarse and fine deposits is quite regular, and gravel beds may extend as far as 10 miles from land. Waves and currents sweep sediment not only toward the shore but parallel with it, and tend to simplify the coastline by building barriers and spits across the mouths of bays, which the waves may pile up above high tide, as is seen along the eastern coast of the United States. Behind these barriers, streams bring in sediments, filling up the bays and converting them into salt marshes, and eventually into land. Very near shore currents produce irregularities of stratification, especially the structure known as cross-bedding. Nor are the deposits of lime which go to make limestones deposited at the bottom of the sea by organic forms, with calcareous exteriors, such as shellfish, starfish, and the coral polyps, to be forgotten. For example, the chalk white cliffs of Dover, which are so characteristic a feature of the coast of the south of England, are composed mainly of tiny shells, many of them so unbroken that they can be picked out by hand, while the whole structure under a microscope is seen to be of this order. The creation of huge groups of islands and the extension of the mainland in tropical and subtropical waters by the coral polyp is constant. The fine material derived from the land is generally termed mud. The color of the mud is different on different parts of the ocean floor. It is blue, red, and green, according to the prevailing coloring matter. The abysmal deposits are those the materials of which are not directly derived from the land, but consist of matters carried to the sea in solution and extracted from the seawater by the agency of organisms, together with volcanic substances in a more or less advanced stage of decomposition. They are generally termed oozes, the most important of which is foraminiferal ooze. The foraminifera are minute animals, each one a tiny speck of jelly, most of which, in spite of their extreme simplicity of structure, have the power of secreting very beautiful and complex shells of carbonate of lime. As the animals die, the shells settle to the bottom in myriads. Silica is also dissolved in seawater, and various organisms construct their tests of that substance. The radiolaria are, like the foraminifera, a group of microscopic, unicellular animals, which secrete siliceous tests of the most exquisite delicacy and beauty. They live both at the surface and at the bottom of the sea. Radiolarian tests may be detected in all sorts of marine deposits of both deep and shallow water, but it is only in very profound depths that they occur in quantities sufficient to give character to the deposit. In the Antarctic Ocean there is an extensive belt of diatom ooze, resembling the freshwater deposit, but may be distinguished by the presence of foraminiferal and radiolarian shells and tests. The profoundest abysses of the ocean, far from any land, are covered with a deposit of red clay, which, though varying much in composition and color, is yet of a quite uniform character. The clay is derived from the disintegration and decay of volcanic substances, especially pumice, which floats upon water, often for months, and drifts long distances in the ocean currents. Of all the oceanic deposits, the red clay is the most widely extended, covering 51,500,000 square miles of the bottom. The excessive slowness with which this abysmal deposit is formed is shown by the occurrence in recognizable quantities of meteoric iron. Comparing the marine deposits now accumulating in the sea with the rocks of evidently marine origin which form most of the land, concludes Scott, we find that the great bulk of these rocks, the sandstones, slates, and limestones, are such as are formed in water of shallow and moderate depths, while only rarely do we discover a rock that implies really deep water. End of section 19.